When installing current transformers, also known as ET, in a cabinet for metering, it is important to twist the secondary wiring. The reason for twisting the wires is primarily to mitigate the effects of electromagnetic interference and to enhance the precision of the measurements that are being taken. Electromagnetic interference, or EMI, can originate from various sources, especially other electrical equipment and nearby wiring within the vicinity of the current transformers. The act of twisting the secondary wires plays a crucial role in establishing a balanced circuit. This balanced configuration helps to neutralize the impact of electromagnetic interference. When electromagnetic interference is present, it can induce currents within the wires. However, because the wires are twisted, the induced currents are equal in magnitude but opposite in direction. This causes them to effectively cancel each other out, which reduces the overall impact of the interference on the signal. In addition to mitigating the effects of electromagnetic interference, twisting the secondary wires contributes significantly to improving the accuracy of the measurements obtained from the current transformers. It achieves this by diminishing the impact of inductive coupling. Inductive coupling becomes a factor when the secondary wires are positioned parallel to each other over a considerable distance. In this arrangement, the wires can behave similarly to an inductor, potentially introducing errors into the measurement process. Twisting the wires serves to minimize inductive coupling by reducing the extent of parallel runs between the wires. The process of twisting the secondary wires requires careful attention to detail to maximize its effectiveness. Firstly, the twist should be executed tightly and uniformly along the entire length of the wire. Secondly, a recommended rate of twisting is approximately 5 to 10 twists per foot. This frequency of twist ensures that the interference and inductive coupling effects are adequately minimized. Thirdly, it is essential to maintain a consistent direction of twisting throughout the entire length of the wire run. This consistency helps maintain the balanced nature of the circuit and ensures effective cancellation of induced currents. By adhering to these guidelines during the installation of current transformers, one can ensure that the equipment operates optimally and that accurate and reliable measurements are obtained. Firstly, let's discuss electromagnetic interference in more detail. Electromagnetic interference is a disturbance caused by electromagnetic radiation emitted from external sources that affects an electrical circuit by electromagnetic induction, electrostatic coupling, or conduction. EMI can disrupt, degrade, or limit the effective performance of the circuit. In the context of current transformers, EMI can introduce noise into the secondary circuit, leading to inaccurate readings. The twisting of the wires effectively reduces the loop area, which minimizes the antenna effect of the wires, reducing their susceptibility to picking up EMI. Secondly, let's elaborate on the concept of inductive coupling. Inductive coupling occurs when two or more conductors are placed in close proximity to each other, allowing energy to transfer from one conductor to another through the electromagnetic field. In the case of parallel secondary wires, the current flowing in one wire can induce a voltage in the other wire, and this is known as mutual inductance. This mutual inductance can cause errors in the measurement of the current being transformed. Twisting the wires reduces the parallel length and changes the orientation of the wires, thereby minimizing the effect of mutual inductance and improving the accuracy of current measurement. Thirdly, the tightness and uniformity of the twist are critical. Loose twists or variations in the twisting rate can lead to inconsistent cancellation of EMI and uneven reduction of inductive coupling. The tighter and more uniform the twists, the better the balance and symmetry of the circuit, which further reduces the effects of interference and inductive coupling. Fourthly, the recommended twist rate of 5 to 10 twists per foot is a practical guideline based on the trade-off between the effectiveness of interference reduction and the ease of installation. A higher twist rate provides better interference reduction, but can make the wires stiffer and more difficult to handle. Fifthly, maintaining a consistent direction of twisting is crucial for ensuring that the induced currents in the wires cancel each other out effectively. If the direction of twisting changes, it can disrupt the balanced nature of the circuit and reduce the effectiveness of interference reduction. In practical applications, it's also important to consider the following factors. 1. the selection of appropriate current transformers should be based on the specific application requirements, including the current range, accuracy class, and burden rating. 2. The wiring of the secondary circuit should comply with relevant electrical codes and standards, such as the National Electrical Code, or NEC. 3. The secondary circuit should be properly grounded to ensure safety and to minimize the effects of ground loops and common mode noise. 4. The use of shielded cables for the secondary wiring can provide additional protection against electromagnetic interference, particularly in environments with high levels of electrical noise. 5. Regular inspection and maintenance of the current transformers and the secondary wiring are essential for ensuring continued accuracy and reliability of the metering system. Here are some additional points to consider regarding the installation of current transformers in their secondary wiring. Firstly, consider the burden resistance. The burden resistance is the total impedance connected to the secondary winding of the current transformer. It includes the resistance of the metering instrument, the connecting leads, and any other devices connected in series with the secondary winding. The burden resistance is an important factor in determining the accuracy of the current transformer. If the burden resistance is too high, it can cause the current transformer to saturate, which can lead to inaccurate readings. Secondly, ensure proper grounding. Proper grounding of the current transformer and the secondary wiring is essential for safety and to minimize the effects of ground loops and common mode noise. The grounding conductor should be connected to a reliable grounding point, such as the equipment grounding bus in the electrical panel. Thirdly, consider shielding. Shielded cables can be used for the secondary wiring to provide additional protection against electromagnetic interference. The shield should be connected to ground at one end only to avoid creating a ground loop. Fourthly, use the correct wire size. The wire size used for the secondary wiring should be appropriate for the current carrying capacity of the circuit. The wire size should also be selected to minimize voltage drop in the secondary circuit. Fifthly, proper termination is key. The secondary wiring should be terminated properly at the current transformer and at the metering instrument. Use appropriate connectors and ensure that the connections are tight and secure. Sixthly, consider testing and calibration. After the current transformers and secondary wiring have been installed, it is important to test and calibrate the metering system to ensure that it is operating accurately. This can be done using a current injection test set or other suitable testing equipment. Let's delve further into the practical considerations for wiring and grounding CT secondaries. One aspect to emphasize is adherence to local and national electrical codes. The National Electrical Code, specifically Article 310, addresses conductors for general wiring. Table 310.15b16 typically provides ampacities for insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air. This table is used for determining the appropriate conductor size based on the anticipated current. When wiring CT secondaries, you must ensure that the selected conductors meet the ampacity requirements for the application. Another factor is the voltage drop. While CT secondaries are designed to output current proportional to the primary current, excessive voltage drop in the secondary wiring can affect the accuracy of the metering. Voltage drop is more pronounced over longer distances or with undersized conductors. The formula for voltage drop is volts drop equals current times resistance times length. To minimize voltage drop, select conductors with low resistance and keep the wiring runs as short as possible. Proper grounding is paramount for both safety and performance. The CT secondary circuit should be grounded at only one point to prevent circulating ground currents, which can introduce errors. Typically, the grounding point is at the metering device. The grounding conductor should be sized according to the NEC, often referencing Table 250.122, which provides minimum sizes for equipment grounding conductors for grounding raceway and equipment. Shielded cables can be employed to mitigate electromagnetic interference, especially in electrically noisy environments. The shield should be grounded at one end only, typically at the metering device, to avoid ground loops. The shield acts as a barrier, intercepting electromagnetic noise and shunting it to ground. Care must be taken when routing the secondary wiring to avoid sources of interference such as high voltage conductors, variable frequency drives, or switching power supplies. Keep the CT secondary wiring physically separated from these sources or use conduit to provide additional shielding. For connecting the CT secondary wiring, use appropriate terminals, connectors, and junction boxes that are rated for the application. Ensure that all connections are tight and secure to minimize resistance and prevent overheating. Regular inspection and maintenance of the CT secondary wiring are essential to ensure long-term reliability and accuracy. Check for loose connections, damaged insulation, and signs of corrosion. Periodically test the CT and metering system to verify their accuracy. Moreover, shorting blocks are crucial safety devices for CT secondary circuits. Never open circuit a CT secondary while the primary conductor is energized, as this can generate dangerously high voltages. Shorting blocks provide a safe means of short-circuiting the secondary during maintenance or testing. These blocks should be installed close to the CT and operated whenever the secondary circuit is disconnected from the metering device. Consider the physical environment when selecting CT and wiring methods. In corrosive environments, use corrosion-resistant CT, conductors, and conduit. In high-temperature environments, use conductors with high-temperature insulation ratings. Also, be aware of any specific requirements or recommendations from the CT manufacturer regarding wiring and grounding. Proper documentation is critical for CT installations. Keep detailed records of the CT specifications, wiring diagrams, grounding locations, and test results. This documentation will be invaluable for future maintenance, troubleshooting, and upgrades. Firstly, the selection of the correct current transformer is paramount. The CT ratio, accuracy class, and burden rating must match the specific requirements of the metering application. An incorrectly sized CT can lead to inaccurate measurements and potential damage to equipment. Secondly, the routing of the secondary wiring is a critical aspect of the installation process. The wiring should be routed in a manner that minimizes exposure to electromagnetic interference. This often involves using grounded metal conduit and maintaining a physical separation from high-voltage conductors. Thirdly, the use of shielded cable for the secondary wiring can provide an additional layer of protection against electromagnetic interference. The shield should be properly grounded at one end to prevent ground loops, which can introduce noise into the measurement circuit. Fourthly, the termination of the secondary wiring must be performed with care to ensure a reliable and low-resistance connection. Loose or corroded connections can introduce errors into the measurement and potentially cause overheating. Fifthly, the grounding of the CT secondary circuit is a critical safety measure. The secondary circuit should be grounded at a single point to prevent circulating ground currents. This grounding point is typically located at the metering device. Sixthly, shorting blocks are an essential safety component in any CT installation. These devices provide a means of safely short-circuiting the CT secondary during maintenance or testing. Never open circuit the CT secondary while the primary conductor is energized, as this can generate dangerously high voltages. Seventhly, the burden resistance of the secondary circuit must be carefully considered. The burden resistance is the total impedance connected to the secondary winding of the CT. If the burden resistance is too high, it can cause the CT to saturate, leading to inaccurate measurements. Eighthly, regular inspection and maintenance of the CT installation are essential to ensure long-term reliability and accuracy. This includes checking for loose connections, damaged insulation, and signs of corrosion. Ninthly, proper documentation of the CT installation is critical for future maintenance and troubleshooting. This documentation should include the CT specifications, wiring diagrams, grounding locations, and test results. Tenthly, the use of calibrated test equipment is essential for verifying the accuracy of the CT installation. This includes current injection test sets and digital multimeters.